Thank you. All right, everyone, welcome to the last formal full day, as Scott just said. We're excited and we're going to get into this real quick. We have an extra readout. So we're going to start with, let me roll up the readout for knowledge-informed machine learning. Frank, do you want to take it away?
Yep, can you hear me?
Yes.
And then the challenge of sharing screen, let's do that.
And we'll do coastal dynamics next.
How does this, can you see this?
Screen. You're set.
Okay. So I'll be very brief. Thank you for allowing me to talk today after I made a mistake scheduling on Monday, so I appreciate it. So I'm going to give a very brief overview of the knowledge-informed machine learning and reminding you, we broke this out into three areas: scientific type knowledge, world knowledge, and expert knowledge. But let me give you a little bit of a slide on what we think the benefits are of this approach. And actually, there's a lot of overlap, I should say, or I may say a few times in this short talk, that there's a lot of overlap between this session and several of the other cross-cutting sessions, especially since they're all related to, in some sense, to learning, and it's hard to disentangle these. So knowledge-informed machine learning, among the reasons to do it is to make the most of the data that you have and use, and in particular, use the data that you have in other forms of, use the knowledge that you have to help in data sparse situations. I often say that despite the fact that we have a lot of data and a lot of problems, and the data may be large in the bits, that number of bits and so on, for the complexity of the problems we're looking at, it may actually be sparse. So we expect this to improve it. It will improve these situations when the data is sparse as it is. It will improve we believe it will improve generalization by using physics as a regularization. By physics, I mean physics and chemistry and all the other processes that one models. It's also important in terms of giving performance guarantees on stability of solutions, it'll satisfy constraints and provide a notion of uncertainty and so on. It is easier in many cases if one involves knowledge in the training, extra knowledge in the training in terms of interpretability and explainability, but also in the area of reproducibility, and Lynn may touch on that when she talks. It's important to have models that are learned, not just memorize the data, but also be physically consistent and respect the laws, again, of physics and chemistry and what's known about the processes. Also, using knowledge-informed machine learning can help the acceleration and the convergence of the learning process, which itself can be extremely expensive computationally and again require a lot of data. And this is all very important in terms of using, having better resource allocation to solve the specific problems that we're looking at. So those are the benefits. Let me just remind folks that, as I said, you could have broken this into a number of ways. We broke it into the same taxonomy that Van Rooyen and all did in terms of scientific knowledge. These are things such as algebraic and differential equations, evolution equations, results of simulations, and so on. World knowledge, this is the knowledge of the particulars of the data. So for example, if there's spatial invariances, if there are particular logic rules, if you have a notion of how things are coupled and interacting with each other in terms of knowledge graphs and so on. And then finally, expert knowledge, which is captured among the types of expert knowledge are probabilistic relationships, human feedback, and so on. And so we had three sessions. We broke out into three parallel sessions, broke out into each of those, and in each of those discussed a number of things: grand challenges, open research, next directions, and so on. And given the brief amount of time, I'm just going to go over very briefly the grand challenges that we came up with. And again, I suspect, or I know these are similar grand challenges that showed up in many of the other cross cuts and probably will show up today in some of the other talks. So one of the grand challenges is how do you encode uncertainties in the learning process and then propagate that through multiple events in multiple parts of the learning process? That's still an open question. There are some ideas there, but it's open, especially for the systems that are as complex as the climate and Earth systems. How do you involve domain knowledge across multiple different spatio-temporal scales? It's challenging enough even at one scale, but when you have to start looking at coupling things from a variety of different scales, it becomes even more challenging. As I said before, making the most of sparse and or inaccurate domain knowledge. I mean, how do you do that? And we believe there are two approaches. One is really developing via transfer learning, where you learn from the data from one system that is closely related and use that to help learn, to help make predictions in another system. This has actually turned out to be extremely useful in natural language processing. The question is, how useful is it in physical systems? And because we have equations, we think there's a lot more you can do in terms of proving closeness of distributions and so on. And then the other component, which falls out, is related to transfer learning, is generating synthetic data, again, based on domain knowledge. And actually, this is closely, in my opinion, is closely coupled with what Nathan was talking about on for surrogate models the other day. I think what's really needed, we think what's really needed is developing a theory for combining these various types of knowledge. Again, there's some work out there, but how to do it with all the extra challenges, uncertainties, scale, bridging, et cetera, that and different types of multimodality that shows up in Earth systems modeling. That's a wide open area. How to accelerate the actual learning process, in particular hyperparameter selection. And that becomes very challenging. A lot of this is done by hand, and that's not a scalable solution, especially for very large scale systems where you have to train on very different types of data, multiple sources, and so on. Another grand challenge is how to determine, represent, and incorporate emergent complex constraints. So not only, you may not have the constraint at the so-called microscopic level, but you have to, things may emerge that are naturally impossible, and those should be, there are constraints on emergent properties that should be obeyed as well, and that's a wide open area of how to do that. And then and then extracting complex relationships from climate model output, doing that in an automated way. There are some really nice tools that just came out, in fact, for proving theorems in knot theory in terms of learning complex relationships from large scale data. And so I think there's a lot of work in that area that's very exciting, and a lot of possibilities in climate science. Generalizing beyond observed data, machine learning methods tend to work really well for the types of data you've seen. This is not unrelated to the transfer learning method above, but how do you generalize to regimes where you don't have the training data necessarily? And then some real grand challenges in terms of practicality are creating composable software environments so that you can integrate all these different types of data. And then finally, a grand challenge, again, which I think is ubiquitous here, is developing a rigorous practical framework for optimal resource allocation, that is observation, experiment, et cetera, again, gathering data of different types, integrating data of different types, and then using that and driving that in sort of in a goal-driven way for decision-making in large-scale uncertain complex systems such as Earth systems. And with that, that's a brief overview of our session. So thank you.
Great, thank you, Frank. All right, next we're going to do coastal dynamics, oceans, and ice. And Matt, I don't know if you or Paul were going to kick this off.
Paul's going to kick it off.
Okay, Paul, feel free to share your screen and take off.
All right, and we're off and running, I think. So hopefully folks can see.
I can see you. All right, you're good.
Yep, excellent, great. So first up, just thanks to everyone that was involved in this session. It's been a really interesting opportunity to talk about a whole bunch of different interesting things, and it's been great to engage with everyone. So hopefully I can steer through. So I'll start out just with how the session was run. So first up, we had 3 invited talks, which were targeted at these kind of 3 different kind of foci. So coastal, Clint Dawson gave a really interesting presentation, actually, which kind of kicked things off. Mika Sonnenwald provided an overview for the ocean focus. And that was, again, it's just been really good. It really kicked off a lot of discussion, actually, which really set the session up for success. And then Alex finished up with a nice focus session at presentation at the end. We started out with 115 attendees, and there was a lot of engagement, actually, even at the very beginning in these invited talks. And it was great just to get everyone thinking and talking about things. So next out, we had breakouts, and we had 6 of these broken into the different sessions. You can see, and you can see the chairs and the rapporteurs listed there as well. So coastal physical, coastal human and sea level, marine biogeochemistry and inland connections, an ocean focus, a sea ice focus, and a land ice focus. And we started out with 115 attendees to the invited talks, and we ended up with 103 attendees. So I think there was a lot of engagement, and people really hung around and engaged the entire way through. So it was a real success, I think. So the word cloud of grand challenges is contributed by the attendees to the session. You can see some familiar kind of foci here. So uncertainty quantification, hybrid modeling, the digital twin, model accuracy, a whole bunch of kind of things that really resonate pretty strongly, I think, with a lot of the other sessions that have summarized, where we could go with this, what are the challenges. Current state of the science, the neural network was one of the kind of key things that really jumped out a lot. and deep learning. And when we polled the attendees to the session, these were some of the things that really jumped out again. So the neural networks was one of the most common techniques that have already been applied. Models, emulators, surrogates, generating parameterizations using ML, and then data synthesis and gap, filling, extrapolation, interpolation of data, and then some other additional ones as well. So we then polled the attendees about, what would be the potential impact, and it was less clear in this community what AI ML will be doing, where we're going to be going. I think there's a lot of opportunity, but because there's so many opportunities and so many things that we could achieve, it wasn't totally clear as to one key thing that will be the primary impact of this on the field. So if we summarize them down just to the grand challenges, many of these things I think resonate with what Frank presented just before, and actually what was presented in many of the summaries of the previous breakouts too. So again, this multi-scale representation, we lack a multi-scale theory, and so how do we do this? And trying to balance the competing priorities of resolution versus parameterization. Is ML a way of being able to investigate this space and really trying to tease out what we need to go after when it comes to, say, setting resolution for model components. One of the things that it's a grand challenge in some senses, but it's also something that runs in, I think, parallel to grand challenges, which is really trying to use the existing tools, standards, data in a more consistent and comprehensive way. So the way that this was kind of brought up in the session was we need better standards. We need to kind of really start thinking about how we can accumulate all of this knowledge by cleaning up the way that we write and execute code, the metadata that we have across the realms, for example. And this is, not just the ocean and ice, this is something that extends back into soil, a whole bunch of different things across the Earth system realms. So test databases or having training data sets, some of these things that, we really are in a situation where we've got a lot of information, a lot of data available to us, but we need to better organize ourselves so we can leverage those into machine readable AI ML ready tools, and then also metrics as well. So basically trying to really think about this across the community and figure out ways of really leveraging what we've already got. So the other thing that we have too is another focus of extremes prediction and tipping point threshold identification as a grand challenge. The other thing that these realms share is sparse data coverage. So we don't have perfect observations, and we really need to pay attention to those as we really push the modeling resolution into resolutions that we just don't have observations for as well. So are there ways of using ML to try and extract more information from our existing observing networks and giving us insights as to how we should really try and push the generation of next generation observing networks as we go further forward? So another thing that kind of popped up, particularly in some of the human focused breakouts, was the human responses. What we're going to do, are there ways of using ML AI to try and really tease out ideas about what potential scenarios could be? Are there kind of cheap AI ML ways of trying to extract information from the information, the data, the models that we already have, which don't require the full physics, which means that we can get a lot of different, build a real PDF of what likely scenarios could be. Improving the model data ensembles. And so this is observations and then model ensembles as well through learning. So really trying to extract more information from the data that we have. Increasing interpretability, so dumb learning, ways of trying to build more confidence actually in the AI ML tools that exist. So big data, but simple insights, really trying to extract the signal from the noise and the signal from the big data. And then there was some specific kind of realm foci things. So, there was information about ice sheets, for example, ocean. One of the things that came out in one of the sessions was combining the physics to the chemistry biology. So we've got these kind of different communities that we need to connect. And are there ways of using AI ML to do that and really investigating the non-linearities, which may be present in these different connections. So then just to summarize the next steps. So these are broken down into the more specific near-term ones, and then we had these kind of overview ones for the medium to long term. So one of the key things that just kept repeating, I think, is building stakeholder trust in AI/ML. So can we reproduce explainable science with explainable AI? So engage and develop trusting relationships and trust in these tools so that we can, use these tools and trust these tools as we go forward. Another thing that came out too was trying to understand the decision-making process of stakeholders. So trying to figure out what the best way of engaging with stakeholders is, and how can we use AI/ML to get us to a point that we're actually doing a better job of the communication and answering the questions that really matter. Another thing that really resonated was building communities and teams. So I think one of the things that's been very clear to me across these multiple sessions is we've got these fragmented sub-communities that really want to engage, but we're not really certain as to how to do that best. So we've got the climate science, the data scientists, we've got modelers, we've got observationalists, we've got the hardware developers. And one of the ways that we'll probably be able to do that is trying to move into a culture shift where we really facilitate a bottom-up, the early career tech-savvy folks, and engaging them and facilitating them to really kind of, build these connections together is the way we're going to have to really move this forward. We need the right personalities to work across domains. We really need to have, excited, minds that have a lot of energy that really want to try and make connections and then build communities around those. We need to define important but manageable problems to kind of kick the process off, to engage folks, and then to build these domains and communities. And then also create opportunities, spaces, and programs for interaction. So there's some examples there of the Kavli Institute. But the other question would be, what can AGU, AMS, or even DOE do to really kick along this, making spaces, creating opportunities for these different sub-communities to come together and really try and tackle big challenges. Again, this data standardization and availability. So what can we do better with what we've already got? So, thinking about metadata, test training databases, metrics, reducing the data wrangling. Are there ways of really trying to, bring many of these different disparate data sources into a framework that really facilitates their use in a machine readable way? And then a key thing also is infrastructure support. How do we do this? How do we set up, data archives, computing resources that really facilitates the community to engage and not, duplicate effort across the communities? So leveraging and extending existing standards, the CF metadata standards, CMIP data is a huge resource. It's something that we've got as an example to kind of follow. And then also recognizing the importance of the standard developers and these operational folks that are absolutely essential to making anything happen. But often they're kind of doing this work behind the scenes rather than, doing work in the PI kind of space. And then opportunities with data model fusion. So some of the things that popped out were parameterizations, and then also using AI/ML for low-cost surrogates, trying to really tease out information from the data that we've got. And then again, this scenario discovery selection. So that just kind of came back to the opportunity here of trying to really understand, what are the likelihood scenarios of different choices that, humanity might make. And then, excuse me, the medium term and long term, scale-aware parameterizations, the idea of kind of continuous integration, improvement, learning. So really trying to optimize this situation so we're building a continuous learning model. Uncertainty characterization, propagation, and identification. And then thinking about ML as a coupler across different things. And one of the realm-specific examples was the ice sheet models and the Earth System models. Are there ways of using ML as a way of connecting these different things? Model tuning is another opportunity. And then also AI for smart platforms and instruments. So are there ways of trying to use AI/ML to extract more information from the observations that we have, the platforms that we have? Can we inject AI/ML into, optimizing, for example, the Argo float, where we're really targeting phenomena by using AI/ML to try and extract more from the existing observing networks. and then also incorporating human feedbacks. And then that's it.
Great, thank you, Paul. All right, let's move to knowledge discovery and statistical learning. Xingyuan, are you ready to share? There you are.
Can you see the screen now?
Yes.
Okay. So in our knowledge discovery and statistical learning session, I first would like to give a big shout out to our co-chair, Richard Mills, and all the other breakout room discussion leads for bringing this session together and running it successfully. So what our session really is about is to re-image, what's the future of traditional machine learning methods like regression, supervised and supervised classification, model reduction, density estimation, that line of methods in the era of the deep neural networks. And we also discussed, what's the use of the Bayesian statistics in this new era in terms of uncertainty quantification and reduction, and in bringing all the data together, and also bridging across the different scales. So in our session, we started with 3 invited presentations on statistical challenges in uncertainty quantification for massive remote sensing datasets, machine learning and climate risk assessments, also on probabilistic machine learning and subgrid modeling. So that set us up for our breakout discussion. We actually we have 7 breakout rooms, one on data assimilation, one on scale bridging, and the others on data fusion, data model reduction, statistical learning, unsupervised learning, and also on uncertainty quantification and sensitivity analysis. I would also like to mention, we employed an ensemble of note-taking tools like Jamboard, Google Doc, Google Slides, after mining what the other sessions had done before us, which was really effective and also very fun. And what we have summarized from the great discussions we had across all those 7 rooms are, in terms of grand challenges, it's really hard to track and quantify uncertainty in the coupled Earth System model predictions that are subject to a large number of different types of uncertainty. And the ensemble simulations of Earth System models are very computationally expensive, while our, uncertainty quantification methods and data assimilation, they often require that large number. There's lack of harmonization for data coming from different sources, and lack of uncertainty information generally in those data products we have access to. There are not many methods that are available to help us propagate uncertainties through the coupled model components and through the AI machine learning model pipelines. We are facing the challenge to account for the increased nonlinearity and non-Gaussianality for complex models. And it's very hard to detect the anomalies, especially the extremes under the highly non-stationary climate as well. So we need an automated and unsupervised discovery of causal relationships underlying a complex system from all the data available to us. We found it challenging to use machine learning to discover the governing equations we often seek for, and hard to go beyond the gradient-based methods in machine learning. And lastly, dealing with the imbalanced data to train machine learning models is also a common challenge we face. Then in terms of state of the science, we feel the clustering methods are well established for eco-region delineation or watershed zonation, this type of classification applications, as well as for linear dimension reduction approaches are also well adopted. And Gaussian process models are widely used in Bayesian statistics or in all uncertainty quantification related applications. And the current sensitivity analysis and the UQ efforts usually focus on the regional case studies or only involving a subset of model components, or subset of uncertainty sources. What's emerging and are like the surrogate methods are being used to reduce computational cost for model calibration, uncertainty quantification, and sensitivity analysis. And we also have been using AI-based approaches to replace parameterization and to develop like multi-resolution modeling across different domains too. The other thing noticed was like data harmonization currently is mainly done manually. So to address all those challenges, we think the opportunities that are existing for us, first is to create model output like gridded data set based on observations from multiple databases and gap fill them. It would be great to adopt multi-fidelity sampling methods to our domain on top of multi-fidelity modeling approaches we often are more familiar with, and use existing machine learning methods to bridge scales to develop super resolution models, and to use existing surrogate models to assist parameter calibration is still a great opportunity for us. And use clustering or other unsupervised techniques to gain insights from large data sets and combine that with a probabilistic interpretations or inference to help us better quantify the uncertainty. There's also opportunity to apply the semi-supervised methods to mine the data sets with a few labels. And I just want to quickly jump to say there's opportunity to apply like data-driven methods to resolve potential biases in our physics-based models and to aid the data collection with those like edging technologies to close the MODEX loop. So what research must be done to address the challenges? There are like need to develop AI-ready benchmark data for testing multiple techniques. We need metrics to evaluate model fidelity to standardize those approaches. And we need more reference implementations or examples to help us learn those methods, and active learning and optimal experimental design to close the MODEX loop. We also need the overall modeling strategy that can combine multi-fidelity models. And we need UQ in like deep learning or machine learning models to help us quantify the overall uncertainty. And we need like stochastic parameterizations for subgrid variability, and need more effective dimension reduction approaches beyond the principal component analysis. And we think the great opportunity in the data assimilation alike algorithms for training machine learning models using like numerical simulations to generate training data. So what next? Now we can start with building test beds for prototyping, benchmarking, all those different mixture of methods. And we should enhance the communications between data, math, and domain scientists, and develop density estimation methods for non-Gaussian distributions. And we need to start dealing with the curse of dimensionality and enforcing the physics constraints in machine learning models and address the data sparsity. And in the 5 to 10 year frame, we need develop UQ methods for deep learning models and enhance modularity in hybrid modeling approaches. And we should learn causal relationship, develop methods to learn causal relationships from our data and model. And a bit further, we should explore exascale computing, and we should build the complete pipeline as an integrated infrastructure for blending machine learning with others. With that, we can routinely deploy machine learning methods in the, and explore the full data records from what we have. So with that, thank you. And yeah.
Great. Thank you, Xingyuan. Appreciate it. All right, next up, climate variability and extremes. Maria, I think you were going to start, but if not, please correct me.
Yes, I can start. I'll go ahead and share screen. Okay, perfect. Hello, everyone. So my name is Maria Molina. I work at NCAR, and I'd like to acknowledge my session co-lead, Travis O'Brien from Indiana University, who will be also presenting with me today. And we also want to acknowledge our session co-chairs, and their names will be acknowledged in the following subtopics that will be discussed. But before jumping into subtopics relating to climate variability and extremes, we wanted to share with you the answers to several poll questions that we presented to everyone that attended our session. And so the first one on the top left is a word cloud, and we asked people to tell us or provide us with words for the Earth system components that can come to mind when they think about climate variability and extremes. And we can see that we have a range of scales covered here, both spatially and temporally, including oscillations on subseasonal to seasonal timescales or longer, and even some very fine scale features such as tornadoes, so also looking at extremes. But overall, the ensemble of machines known as our brains do tend to, with greater frequency, identify Earth system modeling components, which I thought was interesting, such as the atmosphere, ocean, sea ice, and land. We also polled participants on what machine learning methods or the applications that they use with greater frequency were. And so overall, we see that in large part, a large portion of participants identified supervised learning, prediction, or classification as their greater use cases. So cases where they had labels associated with input data for training machine learning models. But it'd be really interesting to see how these percentages change over time, and if we see other areas start to gain greater usage in the future. Travis?
Thanks, Maria. And I want to preface this by saying that this session was just 2 days ago. So what we're synthesizing here is very, very fresh, and we've had little time to synthesize it ourselves. So that'll allow us to breeze through these slides maybe a little quicker. So one of the panels led by Steve Klein, Scott Collis, and Juan Restrepo was on climate variability, signal identification, and sources of predictability. And looking through their notes and what's summarized on the slides here, one of the major things that came out opportunities, I guess, for machine learning and AI is the automated discovery of new teleconnections, new modes of variability, that are higher dimensional than just a single variable versus time, and so on. So I think along with that, you can see that there's themes on discovering new sources of predictability, maybe by using machine learning models to make better predictions than we can with dynamical models. Even though maybe at the beginning we won't understand why, we can use that knowledge eventually to gain understanding of where those sources of predictability are coming from and how we can better develop our dynamical models. In general, improving Earth system models through parameterization, bias correction, so on. Gap filling for observations, extending the observational record into spaces and times where we have limited or very sparse observations in order to get better, have a better understanding of long-term climate variability. And then in general, this was actually a theme among a lot of the panels. This was inspired by one of our panelist speakers, Alex Cannon, suggested that it's really important that we start investing in education, and really at the undergrad, grad, and postdoc levels, and also fostering just interactions among different disciplines and so on. So with that, I think I'll pass off to Maria.
Thanks, Travis. So the next subtopic that we have is feature identification and characterization. And so here we have a timeline where we can see progress that we anticipate or what we would like to see over the next 10 years based on attendees for this breakout room. And so currently in the current state, we know that we can already identify numerous types of features such as atmospheric rivers, tropical cyclones using machine learning across data sets. But really looking towards the future, we're really hoping that we can create tools that automatically identify these features, perhaps across different resolutions of data sets, and also very high resolution features that really do pose societal threats and are just quite dangerous, such as tornadoes or lightning storms and ice storms, again, in addition to other fine scale features. And the overall theme as well that was noted here was creating some sort of global catalog of these features. So that could help us better understand or characterize these features and also identify how these features form, right? So for example, tropical cyclone genesis, better, identifying these features in our data sets can also help us with knowledge discovery on some of the processes associated with these features and their evolution over time. Travis?
Yeah, so Maria and I co-chaired the extreme weather predictors and precursors session, and I'm going to mainly focus here on the 10-year section, which is, this is sort of our early draft of our grand challenge questions for this particular subtopic of climate variability and extremes. So one of the big things that we talked about was we just can't do seasonal to interannual predictions very well at this point. And there's a lot of different ways that machine learning might be able to contribute to that, either directly or indirectly in conjunction with dynamical models. And so our hope is that in 10 years, we're going to be to a point where we can do this routinely and well, and to do it with uncertainty baked in. Detection and attribution is, as I think I've heard this phrase a few times in the recent months, we're in the age of emergence of the climate signal. Detection and attribution is going to continue to be a major thing. The general population and decision makers want to know when we have extreme events occurring regularly, what is the effect of climate change on that? And so we think that machine learning could be used for routine detection and attribution as part of a pipeline in conjunction with dynamical models, either emulating dynamical models with machine learning to get larger ensemble sizes, or perhaps using artificial intelligence-based workflows to make the challenge of running post-processing and maintaining climate models, which sounds simple, and it's just not for those of you who've done this, a much more routine, simple thing. One of the things in the earlier part, in the 5 years, that I do want to highlight is, again, this theme of developing undergrad and grad curricula. Well, I know that curriculum development is traditionally in the realm of NSF. I want to argue here that I think DOE could have a very large role to play here in terms of regularly given workshops and symposia for bringing students together from different areas across the US and across the world for training. So Maria.
So our next subtopic is observation model integration. So here, thinking about how we integrate observations, whether globally or regionally, into our models. And so our current state is where we can perform model calibration using machine learning relatively well, and also do gap filling. But as we look towards the future, especially 10 years out, thinking about exascale and distributed and decentralized computing systems, edge computing, and thinking about, again, model and observation integration, and encouraging some sort of interagency collaboration. So Travis just mentioned that a certain topic might be more in the realm of a different funding agency, but hopefully we can see some interagency collaboration here on the attaining and also incorporation of these observations into our models, and also using machine learning to conduct quality assurance and control on crowdsourced observations. While we do have some of that work being conducted now, continuing to see that improving our integration of these observations. And also, I noted that here in the 3-year mark, I really thought this was a very interesting bullet point for designing algorithms for adaptive sampling of models and observations. So trying to design, again, algorithms that can perform these tasks. Travis?
Yeah, and so on the last one, Gemma Anderson and Moet Ashfaq led the downscaling and bias correction session. One of the big things that they talked about in that session was really using machine learning to do downscaling, and not to just produce single point observations, but distributions for downscaling. So uncertainty is baked into the process. And this isn't just necessarily statistical downscaling. I mean, a lot of the discussion was building on existing successes in using machine learning models to emulate dynamical models. So I think this theme of machine learning models as emulators of climate models was a theme that cut across several of our breakouts that I think could be a promising direction to go. And I want to highlight another, I guess for the last bullet point here, standardized methods for online runtime bias correction. I thought that was a cool idea, and I think something that's going to continue to be necessary as we go to larger and larger data magnitudes. it's post-processing after the fact is difficult if you don't store everything. And sometimes in order to bias correct adequately, you need a lot more information than just single two-dimensional variables. So with that, I think that summarizes everything. I'll go ahead and post the link to these slides if folks want to peruse these in more detail at their leisure.
Great, thank you. That brings up a couple of points. One, Siva, I'm sorry that we ran late. You may already be gone, but those of you who are in the session for today for hybrid modeling, please jump over and start that session. We'll continue the readouts here and finish this up. And those session chairs for any session that you've done your readouts, please make sure your slides are in your folder and so that way we can find them and get prepared for tomorrow and have them for write-ups and whatnot. So thank you very much for being on top of that and ahead of the game. Last one we have is explainable, interpretable, and trustworthy AI. Lynn, you're on, but I believe Derek is going to take the lead on this, right? Derek, are you set?
Yeah.
Okay, good.
Yep.
I had that right. Thank you, Derek.
Okay, can you see my screen yet? Does it come up yet?
Coming up. Yes, I can see it.
Okay, cool. All right, so my name is Derek Santos. I'm here to do the readout for the Trustworthy AI session. I want to begin by just quickly overviewing our format that we had. So Lena Pouchard was our chair, and this is a list of our co-chairs. We decided to have no plenary speakers because it was such an important cross-cutting session that everyone seemed to be referencing. So we wanted to spend the maximum amount of time that we could just communicating what the grand challenges were and trying to discuss what is the plan forward. We had 66 active participants, and before we actually began the session, we sent out a poll to ask people what sessions they wanted to participate in, and also kind of just answer those sort of 5 main questions. As a result, we had 5 sessions, 2 on explainable interpretable methods, and then a robustness, reproducibility, benchmarking UQ, and ethics and responsible AI. And again, there's just no way we can cover all the details we covered in these sessions. They were all very productive sessions. So I've just sort of color coordinated this to help guide people's eyes. You can look at these slides later. I'm just going to try and highlight the key points very briefly here. So as the key points, we'll go over real quickly here for XAI. The main takeaway was that we need a scientific framework for explainable AI. So ways to quantify and validate the insights of the actual explainable model that we're getting out, or the interpretation we're getting. In robustness, we want community standards, benchmarks, guidelines, provenance, to promote robust and reproducible machine learning for the Earth System predictability. In UQ, we need benchmarking data sets that are relevant for weather and climate. And then on the ethical side, we need to ensure the community is involved in the development of AI models to ensure that all the stakeholders' needs are ultimately met. On the grand challenges front, I'd say the summary is formalization is what we need. So again, in XAI, there's a lack of a scientific framework, for example, a way to measure the value of an explanation. So consequently, explanations are hard to falsify. It can be justified post hoc, which is not good. And similarly, on robustness, there's no widely accepted community standards, guidelines, benchmarks for promoting robust, reproducible machine learning and AI for the Earth System predictability. In UQ, similar, we need a clear definition for uncertainty metrics to quantify the quality of UQ. And then on the ethical side, we want to know, can we use AI to address data deserts and ensure that it's done in a way that creates environmental justice, right? So there's this problem where data is not uniformly sampled across the world. We don't really understand the dynamics uniformly. So we need to sort of address that issue across the board here. State of the science, I'd say that the takeaway is that many techniques currently exist in other fields that have yet to be leveraged in the Earth System predictability front. I won't go through them all here. I think the important takeaway is that on the ethical side, ethical and responsible, AI for weather and climate is very new. So as a result, they may have to more leverage the techniques from other fields than say like XAI, which has some techniques going, so they're probably more adapt to be able to, they're in a better position to sort of create their more climate specific or weather specific applications. On the opportunities front, I'd say the takeaway is standards and benchmarks is what we need. So benchmark data sets to evaluate the utility of XAI methods for applications in the sciences. Similarly, for robustness, creating community-wide standards, guidelines, benchmarks for robust and reproducible AI, machine learning, and Earth System predictability. On the UQ front, development and data repository workflow benchmarks, application data sets can advance the UQ effort. And then on the ethical side, to that previous point, we need better methods for interrogating the data. For example, discovering where we need more data for where these data holes exist. I'd say the next steps, the takeaway is pretty much the same. It's standards and benchmarks. I will add, as to the previous group there's this portion about training the next generation of postdocs and researchers, students all across the board. And this should be done in a way that, incorporates this XAI, trustworthy AI, robustness, all these things into the framework just naturally. So it's not something that's done at the very end as like a tacked on at the last step. It's something that is part of the process. And finally, long-term, I'd say the takeaway is consistency and best practices. So in XAI, we need to have best practices in place on what constitutes a sufficient explanation for an AI system and how to best achieve them. In robustness, have highly reproducible and trustworthy AI models for scientific research in Earth System Predictability that will lead to AI-driven acceleration of scientific discovery from the field. And then lastly, on the UQ front, the co-design of models that exploit the advances of new forms of computing, such as quantum, neuromorphic, and exascale. And with that, that's the very brief summary. Thanks, everybody.
Great. Thank you for doing that. And thank you for doing it so quick. I appreciate it. Everyone, thank you for your attention. I've actually put a link in the chat if you want to scroll up a little bit for associated groups for AGU, AMS, and other, because we keep hearing we need to be connected to these groups. We want to try to just grab those if we can, and we'll go from there. But let's jump to the other hybrid modeling session and we'll get started over there. Thanks, everyone.